Hey Scott, if you're talking, I don't think we anybody can hear you.
Can you hear me now?
Yeah.
Okay, that's great. Okay, I guess I will repeat the last several minutes that I was just talking. Anyway, so I just wanted to start off by saying that the grades are posted from the exam that you guys took last Thursday. The grades that you see up there right now are just your raw score. That's just the way that you scored on the exam without any kind of adjustment. There's still a couple of people who had unavoidable circumstances who still need to take the exam, and I can't curve the grades until I have all the grades in to calculate the averages. So those will be curved at some point, probably over the next week. But until then, and I'll send out an announcement once I do that. But until then, you'll just be seeing your raw sort of score for the exam on there. So, any questions about the exam from last week? All good? Excellent. All right. So today, let me get my screen shared here. All right. Hopefully everyone can see that. So today we're going to be, we're going to be moving on to a new topic. And this kind of rounds out the lectures that we've been doing on the individual components of the PCM model of landscape ecology. So of course that's patch quarter matrix, and that brings us to the M in the Trinity, and that's matrices and mosaics. And so we're going to be talking a little bit in more detail about how we understand matrices and mosaics as a composite whole and some of the ways that they can be analyzed. And by the way, I when I was looking this up, I know matrices sounds like kind of an awkward word, but I looked it up in the dictionary. Apparently matrices is also correct. So you can use either one. So I don't know, I've always heard as matrices. So it's up to you, whichever word you prefer. So in order to avoid any confusion though, we will just stick to the singular for now of matrix. And if you remember back to the lecture on landscape structure, the matrix essentially is that background against which the patches, ecotones, and corridors can be identified and understood. And as such, it's typically the largest, most predominant landscape structure in a given study area. Another way to say that is that the matrix is the predominating landscape typology within a given study area when it's viewed at a coarse scale. So as an example, this is a land cover map of Long Island, New York, where I grew up. And for context, you can see the label for Central Park in New York City at the far left side of the image there. And if we look at a study area that's bounded by this yellow box, the matrix would be the predominant and most extensive land cover type, which in this case is urban or dense suburban development. I don't have a key up there for this map, but in this case, that's what red is representing. But if we zoom in on that area to get a better sense of what's going on, at this scale, we can see some of the classification symbology a little bit better. And the urban development appears to be contiguous and homogeneous. But if we look at the corresponding orthophoto of the area, so I'll just flip back and forth here. Whoops. So here's the aerial photo again. And if we look at that aerial photo, we can see that the urban development is anything but homogeneous. And in fact, there's significant differences here in terms of tree cover and intensity of development across that study area. So again, let's go back here. right? So if you look at all of that red area, that's all classified as being urban or dense suburban. But then if we look at the aerial photos, some of it does look like it's very dense urban, but other parts of it look like it's fairly continuous tree cover, and those are probably more suburban areas. So there's a lot of differentiation within even a given classification type. And so even though that this matrix is not a spatially homogeneous landscape, it can still be characterized as a functionally homogeneous landscape with regard to the species or habitat that's being studied. And in this case, we are looking at perhaps a forest species like the eastern chipmunk, or even that wily faux finch that keeps popping up. So when we describe or delineate a matrix, there are three attributes that can be used to describe it. Those are area, continuity, and control over dynamics. So first we'll start with area, and area refers to the spatial extent of the matrix, or another way to put that is the amount of coverage within the study area that can be attributed to the matrix. So by definition, the matrix is almost always the largest landscape typology within the study area. And if we look at our study area here on Long Island again, the area of the matrix would be the acreage within that study area that's covered by red. Continuity refers to the spatial pervasiveness or continuity of the matrix. In other words, a highly pervasive matrix is one that has few interruptions or discontinuities. And continuity of the matrix is inherently at odds with the connectivity of habitat patches and corridors, right? Because the more continuous the matrix is, the less connected the individual patches of habitat are going to be. And so those are kind of two competing forces that we look at when we're measuring and quantifying landscapes. And then finally, control over dynamics refers to the degree to which the matrix is influencing fluctuations of energy and materials across the landscape as a whole. And that in turn is dictated by the proportion of matrix to patch, as well as the degree of contrast between the matrix and the habitat patches, right? So again, that's the two aspects of that are the proportion of matrix to patch. So how much, we know already that the matrix is going to be whatever the greatest land cover type is within that study area, but how much greater is it than the amount of patch, habitat patches, for example? And then also how high is that contrast? The larger that ratio and the higher the contrast, the higher the amount of control over dynamics is going to be. So for example, if we have a really highly contrasting condition, such as this heavily urbanized area surrounding a patch of dense forest, that's going to result in the matrix having a much greater influence over landscape dynamics than a condition that has a lower contrast or a less pervasive matrix. So based on these attributes, several generalizations about the matrix can be deduced. First is that the area of the matrix exceeds the total area of any other landscape element type present, right? That's just kind of in the definition of the matrix, is that that's going to be the most predominant landscape type. Second, the matrix is more continuous or connected than any other type of landscape element present. And finally, the matrix exerts a greater degree of control over landscape dynamics than any other landscape element type that's present, right? So it's the thing that has the greatest total area within the study area. It's the thing that's the most continuous within the study area. And it's the thing that has the greatest amount of control, that's exerting the greatest influence over the overall landscape. And again, those are generalizations, and they're not necessarily true in every single case, but in the vast majority of cases, all three of these are true. And then it's also important to point out that just like with everything else in landscape ecology, the identification of a matrix in a landscape is dependent on scale and spatial extent. Right, so in this example of we have a plan on top there, and then an axonometric below it. In this case, what would you say is the matrix? Does anyone want to take a stab at that? Which landscape type here is the matrix? Kind of, oh, go ahead. Cam, did you want to say something?
I was gonna guess like the darker forest. I'm not sure though.
It could be. It's pretty tough to tell in this one, right? There isn't any one landscape type that's obviously the most extensive, right? And so what that means is that at this scale and spatial extent, it's fair to say that there isn't necessarily an identifiable matrix, right? And in a case like this, you'd be more inclined to use something like the gradient model in order to measure or assess that landscape. In this example of a forest patch, though, that's embedded in a prairie landscape, it's a much more clearly defined matrix based on our criteria of area, continuity, and control over dynamics. And then in that case, we'd be using something, we'd be using the PCM model to assess that landscape, right? So the model that you use to assess the landscape is partly determined by the condition of that landscape and whether or not you have an identifiable matrix. In the vast majority of cases that we're dealing with in landscape architecture, there is an identifiable matrix just because we're dealing with the interface between open space and natural areas and human development. And so there typically is a pretty clearly defined matrix, and that's why we tend to use the PCM model 90% of the time. So in the early days of landscape ecology, the matrix was generally seen as a more or less passive field against which the dynamics of habitat patches and corridors kind of played out, right? So it was just seen as this background that didn't necessarily have a big influence over overall landscape dynamics. But that simplified model, which largely ignored matrix structure, failed to accurately predict species movement and population fluctuations when they began to do field experimentation to see if the model version of landscapes actually lined up with the actual version of what was happening on the ground. And so as a result, matrix function was re-examined to better understand the ecological role that it plays. The term matrix permeability has since emerged in landscape ecology literature to help describe the ease with which various species can move through the matrix when traveling between habitat patches or stepping stones in a corridor, right? So this is thinking about not just, we've already talked about the ease with which species can move through various types of corridors. And now we're talking about when they have to leave those habitat patches or those corridors and move through the open matrix, how easily can they move through that matrix? And that's what matrix permeability is measuring. And then that matrix permeability, in turn, is directly related to the level of contrast between the matrix and the habitat that's being studied. And that's led to the concept of matrix resistance. Right, so a low resistance landscape is one that facilitates high rates of dispersal between patches. So in this case, we have a pretty naturalized condition of some wetland species growing in a low wet area that's surrounded by forest. And this is going to be a little bit easier for a lot of species to traverse because of the fact that even though it's more open than the covered forested area, it's a low level of contrast between the habitat and the matrix. And so that's what we consider to be a low resistance matrix. But then a high resistance matrix, on the other hand, is one that largely inhibits interpatch dispersal of species. So this is where we have a much higher level of contrast. And in this case, we're going from forest to basically mowed lawn. And so that's going to be a much higher level of contrast and a higher resistance to species moving across that landscape. And of course, the measure of matrix permeability and resistance is going to be species specific. It's not going to be the same for every species. Birds that are flying, obviously, are going to have a different measure than animals that are running along the ground. And large mammals, for example, will have a different measure than small rodents. So a matrix that can be easily traversed by some species obviously may be a major inhibition to some other species. And, you know, what might all of that mean exactly when we're thinking about how to assess a landscape? And it simply means that the focus in reconnecting fragmented habitats shouldn't solely be looking at patches and corridors. In some places where habitat reestablishment isn't an option, by properly managing the structural quality of the matrix, you can have a significant positive impact on habitat connectivity just by lowering that level of resistance in the landscape. Does that make sense? Does anyone have questions about that? Okay. Eric, did you have a question?
No, I didn't.
Okay. Okay, and now we're going to look at the overall composition of all of the landscape elements, and that, of course, is the mosaic. So as a reminder, the mosaic refers to that overall spatial and compositional structure of the landscape, with all of the patches, corridors, ecotones, and the matrix functioning ecologically as a whole. When we describe specific landscape mosaics, we do so in terms of three basic attributes: chorology, topology, and character. So first, we'll start with chorology, which is the horizontal dimension of the mosaic. It refers to the types, number, and sizes of the various ecotopes that are present in the mosaic and their geometric arrangement. The chorology is often discussed in terms of concepts such as pattern, scale, connectivity, networks, circuitry, and mesh size, some of which we've touched on before in discussions of the arrangement of things like patches and corridors. And in order to simplify the study of complex landscapes, researchers often break them down into easily identifiable land units using a land classification system. And we've talked about this before. So basically it's taking a complex landscape that has, you know, millions of different types of varieties to it and breaking it down into sort of like types or ecotones and using a land classification system to identify those. So in this case, we're looking at an example that's known as the National Land Cover Dataset, or NLCD for short. And the NLCD is a great source of data for working on larger landscapes, because it's an assessment of the landscapes across the entire United States, broken down into a series of common landscape typologies or ecotones. And you can interact with this data through their online viewer, which is shown here, or you can download the entire data set as GIS shapefiles. So this data can be downloaded, it can be assessed online, and it's great for using with GIS models of landscapes that you're trying to assess. So this viewer lets us not only see land cover, but also change over time, which is really critical because they have data sets that go back to 2001. And they also have things like tree cover and impervious surfaces. So you can get tree cover maps of the United States or of a portion of the United States, the level of imperviousness of the surface for a study area. So it gives you a lot of really useful information that you can use in your analyses. And then the next measure is topology, and that is the vertical dimension. So chorology was the horizontal dimension, topology is the vertical dimension of the mosaic, and that refers to the details of the landscape composition, including plants, animals, soils, and other elements. And then finally, the character refers to a specific attribute of the mosaic that's of particular importance or interest, and that's used to classify the mosaic or landscape type. So terms like forest landscape, agricultural landscape, suburban landscape, like the one that's depicted in this image, this is obviously a suburban landscape, are used to describe the mosaic character. So that's kind of the generalized term that's used to describe the character of that particular mosaic. And typically that's closely linked to whatever that matrix happens to be. So next we'll look at mosaic patterns and how those change over time. And this is a process that's often referred to as shifting mosaics. So from a chorologic perspective, again, that's that horizontal dimension of the landscape. The overall integrity of a landscape can be understood and evaluated in terms of both the pattern of the elements that it contains and the scale at which it operates. And as we've seen previously, one of the most important measures of the ecological health of a landscape is the overall connectivity of the natural systems that are present. So when a sufficient number of corridors is present to become interconnected, we get networks. And from a design point of view, these networks are often used by planners and landscape architects to facilitate or inhibit flows and movements across the land mosaic. Right, so in this case, we can see a number of corridors that are introduced, and they're interrelated to an extent where they're beginning to form a network. Right, so it's not like there's just one line of travel from one patch to another, but in this case, we have kind of multiple options of how to move between patches because we have this interrelated network of corridors that are created between those patches. So if we view this diagrammatically, both of these options have high connectivity technically. Although the one on the right would be far preferable to the one on the left from a conservation point of view, because it has a high level of what's known as circuitry. So circuitry refers to the presence of a multitude of routes available to travel through the network. It's a mosaic pattern that's highly correlated with population persistence and stability. So the greater the level of circuitry you have, the greater the level of population stability you're going to have for various species. And that kind of makes sense because the more options that species have for moving around that landscape, the more resilient it's going to be and the less likely that you're going to have large population fluctuations. Right, so does everyone see that difference in the fact that they're both highly connected? Because you can technically, on the one on the left, you can move from patch to patch. So they're highly connected, but the one on the right has much higher circuitry because there's different pathways that you can choose to get through that network. This is another way of looking at circuitry in a diagram that's more representative of actual landscape geometries. So the presence of the loop in this corridor provides alternative routes between patches, which helps protect the system from natural or human disturbances, right? So this is kind of, what we tend to see more often when we're looking at circuits in landscapes that have been modified by people, right? So in this case, we have the two large patches, a stream channel that has a corridor that's providing a corridor for connection between those patches. But then we also have an area, a secondary area of connectivity. And that's, even though this is kind of a low level of circuitry, it's only providing one alternative. Even just having one alternative is going to provide a much greater degree of connectivity between those patches than having just a single corridor connecting them. And much like with human road networks, intersections in vegetative networks tend to be areas of higher species richness. When we have multiple interior species and each one's traveling on their own route, they tend to mix and cross paths at these intersections, right? So you can think of the circuitry of the landscape as much the same way as a road network would be for people, right? So anytime that you have an intersection, that's going to be a place where there's much higher species richness and diversity, because that's where different species are crossing paths with each other, just like cars traveling on a roadway. And of course, it also follows that any species which are inhibited in their movement by the corridors are going to be much less likely to persist in a landscape that has a high density of corridors. So the density of corridors can also be referred to as mesh size, where a smaller mesh size is equal to a higher density of corridors. Right? So again, species are inhibited. So species that cannot move across those corridors, the species that like to live in that matrix, they are going to have a lower degree of survivability in a landscape that's got a denser mesh. And then enlarged intersections can begin to take on the characteristics of small patches by providing adequate habitat for various species to rest and or breed, which improves the survival rate and viability of a dispersing population, right? So again, these can be thought of as nodes within that network or that circuitry. And these are places where, instead of just kind of moving through as quickly as possible, some species may spend some time there, maybe days or weeks along their journey, because it's large enough to act as a small patch and provide for some of their daily needs. So these connected patches are, of course, likely to have more species and a lower rate of local extinction than an isolated patch of equal size, right? So a patch that's better connected, obviously, is going to have better resilience of the species living there than one of equal size that is not as connected. Now, enemy number one in planning efforts to improve the ecological health of landscapes is, of course, fragmentation. Again, that's the destruction and isolation of previously coherent ecosystems. So efforts around the world right now are aimed not only at stopping and, if possible, reversing the effects of fragmentation, but also working within the confines of human development patterns to try to stitch those fragments back together with corridors, networks, and circuitry to help repair the damage. One of the major problems, of course, with habitat fragmentation is that not only does it lead to a reduction in the total amount of that particular habitat type, but also proportionally leads to a much greater loss of interior habitat, which we've looked at previously when we were studying patches. And the perception of fragmentation might be minimal for wide-ranging animals if the habitat is fragmented on a fine scale, like the example in the diagram on the left. Or on the other hand, it can be perceived as discontinuous to nearly all species if there tends to be a very large scale of fragmentation between those individual patches. Right? So some species that move over great distances, if there's a fine scale of fragmentation like the one on the left, it doesn't make that, quite as large a difference, because they tend to sort of view that as a more or less continuous habitat. But the one on the right is going to be problematic for just about any species. And it's easy to think of animal species such as this brown spider monkey as helpless victims of habitat fragmentation. But in fact, animal species actually play an active role in the dispersal of plant species. And so they can help in the regeneration of habitat that's been fragmented in the landscape. So right now we're going to actually watch a short video that explains how ecologists are partnering with wildlife to repair fragmented forests in Colombia.
The tropical forests of Colombia are home to a myriad of plant and animal species. Like many of the world's forests, this one in the Middle Magdalena Valley is also under threat. As Colombia's human population grows, huge swaths of forest are cleared for farmland and cattle ranches. The remaining patches of forest become fewer and further apart from each other in a process ecologists call habitat fragmentation. Fragmentation threatens the survival of all animals that live in the forest by reducing the amount of habitat and converting what's left to patchy, disconnected areas. That is particularly true for the largest primate in the Americas, the brown spider monkey. They rely on trees for their food and shelter, and a continuous forest canopy acts as a highway, providing them the freedom to move.
The situation with brown spider monkeys in Colombia is very, very critical. They've lost more than 80% of their forests.
It's clear that spider monkeys rely on forests to survive. But do the forests also rely on spider monkeys? Wind, water, or animals can carry seeds from a parent plant to new locations. The seeds of tropical tree species are primarily dispersed by animals that eat fruits.
Many animals eat hundreds and hundreds, if not thousands, of fruits in a day. Most of them will swallow the seeds and will defecate them in other places, and through this process disperse them in different parts of the forest.
Spider monkeys eat large amounts of fruits to support their size and are likely a major seed disperser in Colombian forests. When seeds simply fall in the forest, they end up near their parent tree. Here, seeds compete with other seeds from the same tree. Their chances of survival are low, but seeds that are carried away by spider monkeys and other dispersers are more likely to survive and grow into a healthy plant. Fragmentation reduces forest regeneration in two ways. It decreases the number of seed dispersers, and it limits how far they can safely travel. Andres Link and his colleagues have come to the Middle Magdalena Valley to measure how many seeds spider monkeys are dispersing and from which tree species.
So we started to wonder, okay, what is the role of these primates in the dispersal of seeds of many plant species?
They help to regenerate the forest, and it's very important to know which species are they eating, because in that way we know which species are going to spread and which are not.
The first step is to collect the seeds dispersed by an individual monkey in a day.
And what we do literally is to follow them the whole day long. We see that they're going to defecate, and we pay close attention. But also, normally we hear that some seeds fell, that a monkey defecated, and you can hear it, how it sounds when it hits the leaves in the ground. But when we can't find it, what we do is that we rely on those animals that are specialists in getting to these fecal samples. We just have to stay really still, and in a couple seconds you'll start hearing some buzzing that increases and increases in sound.
The dumbbells have a very particular sound, so you will follow the sound, look for the dung beetle, and they will be making a little ball from the poop that you want. So you will just take it.
Okay, so we have some dung beetles here collecting the poop. So there must be seeds around, and we can find something here. We collect each fecal sample in an individual plastic bag. And we put an individual number to each bag because we're interested in quantifying not only seed dispersal of the species, but also the ability of each individual, or the amount of seeds that it can disperse in a single day, or to find difference between males and females, or in matures and mature animals. A single spider monkey can defecate probably between 13 and 17 times a day, and this is only one monkey, and this will represent hundreds, if not thousands, of seeds that a single monkey disperses in this forest.
They clean the seeds they've extracted so they can be further characterized and cataloged. This work takes place back in their lab in Bogota.
In the Middle Magdalena, these spider monkeys can disperse about 100 species or maybe more. As we learn about the important role of spider monkeys in dispersing the seeds of many plants, and at the same time we see how populations are declining, we start to worry a lot about the future of these forests.
With fewer spider monkeys, the forest is less able to regenerate, further decreasing the spider monkey's habitat. Researchers are trying to break this cycle by replanting the seeds they found. They plant them in deforested areas that are no longer used for agriculture. They will grow into the trees that monkeys need for food and shelter.
So what we do is that we collect those seeds and we plant them in areas that have been degraded. Especially we plant them in areas that we have identified that can be potential corridors between isolated patches of forest.
Growing these trees in the areas between forest patches will allow spider monkeys to move from one patch to another, increasing both their chances of survival and their ability to disperse seeds.
We really think this process of restoration and connecting these forests will provide a future scenario that is much nicer, a future scenario in which monkeys will not depend on us to have a viable population going on there and surviving without the need of our assistance.
So pretty fascinating, right? In terms of thinking about how animals are active dispersers of seeds and how they actually participate in the patterns of vegetation that are created in the landscape. So for any of you who are looking for a career in monkey poop, this is your chance. You can get in on the ground floor here. But it's really interesting. And the fact that they're using a strategy for replanting some of those species that the monkeys tend to eat in order to help with their dispersal, right? So they're being very strategic in terms of thinking about analyzing which species are the ones that they're consuming, and then reconnecting those patches by creating corridors, right? And then the more of a network that they create, the greater the dispersal rate of those seeds, and the more that overall landscape will begin to fill back in with that forest ecotone. So it's a really interesting kind of study and effort at reconnecting some of those fragmented habitats down in Colombia. So we've seen several examples now that demonstrate that landscape mosaics change over time, just like in that previous film. But what are some of the causes of shifting mosaics? So we've seen that one example with the spider monkeys, and there are three principal reasons. These are natural disturbance, ecological succession, and human influence. So in the absence of human influence, a cyclical progression between natural disturbances like wildfires and ecological succession keeps landscape mosaics in a constant state of flux. Ecological succession, for those of you not familiar with it, refers to the progression of plants that colonize a disturbed area in sequence, generally starting with pioneer species such as annual plants and culminating in a climax community such as a mature hardwood forest. And this is a cyclical progression that happens over and over again in natural landscapes, right? And this is something that defines really, particularly Western landscapes where fire is a prevalent determinant of landscape patterns. So you'll have fire come in, it basically wipes out all of the species that are there. And then there are actually some species that are adapted to that fire cycle so that they can only germinate after there's been a fire. There are some species that will not germinate until the seed coat has been broken down by the heat of the fire, and then they can germinate, and those are the first species that begin to take over that landscape that's been denuded of vegetation. When human influence and development patterns enter the picture, it tends to create a much more linear progression and greater fragmentation, as we've seen, as the larger patches are subdivided further and further until there's little or nothing remaining of the original habitat. Right, and this is something that we've seen again and again in some of the different examples that we've studied. And this habitat fragmentation occurs across a variety of scales. So it's important for planners and landscape architects to recognize that relatively small incremental changes can add up to profound impacts over time, either positive or negative. So, you know, things that seem like a minor change today, when that's taken in concert with some of the other small changes that are happening over time, can lead to pretty profound impacts eventually. And understanding that those small incremental changes add up to big impacts, particularly for positive influence on the landscape, for trying to reconnect some of these landscapes, is the kind of vision that's that can be needed when a badly degraded landscape seems like a helpless situation, and thinking about the ways in which some of those landscapes can be restored. So in the early 1990s, there was a famed Brazilian photojournalist named Sebastião Salgado. He was stationed in Rwanda to cover some of the horrific accounts of the Rwandan genocide. And that was an experience that left him traumatized. In 1994, he returned to his parents' homestead in Minas Gerais, I think it's Minas Gerais, Brazil, hoping to find solace in the lush green forests that he grew up in. And instead, when he returned home, he found dusty, barren land that stretched for miles and miles. And in only a few short years, the area had undergone rampant deforestation, which left it fallow and devoid of nearly all wildlife. And in an interview that he did with the Guardian newspaper, he recounted that the land was as sick as I was. Only about 0.5% of the land was covered in trees. And although he was kind of heartbroken to find that level of devastation in his homeland, he set about on an enormous project to try to repair the damage that had been done to the landscape and heal himself in the process. And this image shows the farm that he purchased in the valley, the way that he found it in 2001. And he and his wife, Leila, renamed the homestead Instituto Terra, or Earth Institute, and set about replanting the forests in the area. And the reforestation project, which is undoubtedly one of the greatest environmental initiatives in the world in terms of its scope and its ambition, has also helped to control soil erosion and revive the natural springs in the area. 8 springs, which had once dried up, now flow at around 20 liters per minute currently, relieving the drought-prone region of its woes. And this is what the farm looks like today. That's that same valley that was completely stripped of plants. It's now home to over 500 threatened and endangered plant and animal species. And the Institute, which is still there, now serves as an education center that spreads a message of habitat restoration and assists other local farmers in restoring their lands. So this has been a huge ongoing project now for about 20 years. And it's pretty impressive to see, you know, going back to, right, to what it was 20 years ago, and then seeing it today. And that's just, you know, basically the persistence of a single landowner and, you know, trying to reforest a particular portion of that fragmented landscape. But again, trying to, having that kind of vision that this can be done and having the persistence to do it is really important, and it's making a big difference in some of these landscapes. And there are other individuals who are taking similar steps to try to heal some of these fragmented landscapes. So much closer to home here in the hill country of Texas, David Bamberger was a landowner who set out to prove that long neglected ranch land could be transformed and restored with wildlife, and even restore the groundwater to its former abundance. And so this is another brief video that we'll watch that tells the story of transforming some of this neglected ranch land into a functioning ecosystem.
50 years ago, you couldn't hardly walk through this place. It was wall-to-wall brush. There wasn't any grass. There wasn't any water. Nobody wanted it. On the truck. On the truck. You're the finest dog in the United States of America. Yeah, Texas too. Well, I was born in Ohio, born into poverty, to be honest about it. Lived out in the country amongst the Amish people. So I really got my life example set for me by my own mother. That's where my love of the natural world came from. I've never inherited the nickel, but I inherited a love of the natural world and a respect for it. When I got out of the university, I took a job. I sold vacuum cleaners door to door. I went into the fast food business. I teamed up with a young man, Bill Church, and it was Church's Fried Chicken. And we built that company up to over 1,600 stores, and we sold it. And with that capital, I was able to come here and begin my work on Sela, Bamberger Ranch Preserve. My objective was to take the worst piece of land I could possibly find in the hill country of Texas and begin a process of restoration that would change it back to be one of the best, and that has happened right here. By habitat restoration, by working with Mother Nature instead of against her, and that's what we're all about. 46 years ago, had a drop of water. 7 water wells were drilled, 500 foot deep. Not a one produced any water. The top 125 foot of these hills looks like this. It's Edwards limestone. When the driller drilled all those wells for me, he said, Bamberger, There's one place up here on the top, my bit dropped 40 foot. He said, you got a cavern under there. It's like an auditorium. The only thing about it was, 46 years ago, it had no water in it. It was dry. It was dry because the water that was coming in was running off as opposed to sinking in. When I came here, all of the little holes and all of that limestone were just as dry as the one I'm holding in my hand. Now what happened? We replaced that condition with this condition 2.5 years after we began. The first spring came to life. As we continued on, another spring showed up. We got up to where we had a left. Where did the water come from? It came out of all of that holes in that perched aquifer like that. That's where it come from. It was stored in the earth, and all because of one thing, just one. And I'm telling you, I'm going to show you the greatest conservation tool ever made, and everything I talk about could not have happened without grass. The hill country is just covered with woody species. Primarily, it's cedar. We took out a great portion of it here on the ranch. We were just covered with it. We had no grass. When we took out the cedar and spread native grass seeds, and it began to grow, rainfall then percolated into the earth because of the root system of grass going down. Water percolates in, it fills up your aquifer until the aquifer is full, and when it's full, it has to come out somewhere, and they call that a spring. That spring supplied water for all the nature's critters, plus for all the families that live here, and it even sends water downstream to the city of Boston. What does it cost? Our governments and governments all around the world, they're spending millions and millions of dollars doing all kinds of things, dams and reservoirs and pipelines, and all of this can be done by you and I. You don't have to have government. We can't expect government to do it all anyway. But if we do have some conservation ethics, the results are mind-boggling.
Now, do we see that kind of erosion here?
I'm telling you, truthfully, I've seen this property and the experiences that people have here change lives.
What does SELA mean?
Oh, beautiful. Thank you so much. What does SELA mean? When I was younger, I discovered in the Psalms the word SELA. It means to stop, to pause, to look around you and reflect on everything you see. To me, it's like Thoreau was to Walden Pond. Gives us a chance to say, what's my duty as a steward of this ranch land? And I believe it's to take care of it and to share it. And if you don't share what you have, you're going to live a lonely life. That is a necessary ingredient for every human being, that we need to catch up and live amongst Mother Nature and learn to appreciate her for what she really is. I've given this land to a foundation. It'll go on in perpetuity. It'll never be any different than you see it today. When I leave this world, that's what I want as part of my legacy.
So there are individual efforts like that happening in various parts of the world, and it's refreshing to see that it's not completely hopeless in terms of the situation with landscape degradation, that there are efforts to restore these landscapes, and that, you know, people who are dedicated and have the resources can make a really big difference in a relatively short amount of time. So anyway, restoration efforts like those, they can influence the overall pattern of the landscape mosaic, obviously, which in turn influences the distribution of specialist and generalist species. So when we talk about specialist species, that refers to the ones that are very well adapted to very specific kind of habitat. And they tend to be the interior species that are typically of high conservation value. Generalist species, on the other hand, are the ones that can survive in several different habitats. They're the ones that generally tend to be the edge species that are already kind of overabundant in our landscape. Especially in landscapes of high intensity human development. So why are those generalist species so overabundant in human dominated landscapes? Based on some of the principles we've been talking about earlier.
Lack of predation, maybe?
That's part of it. Think about what fragmentation produces in terms of the types.
Also, so if there's more spatially fragmented areas, larger generalist animals are eat more easily or move more easily through that landscape instead of, you know, a small specialized animal.
They do, and it's not even necessarily size, but the generalists do move more easily through because they can survive in a wider variety of habitats. But it's a little bit more specific than that. Anyone want to take a stab at it? If you think about the proportion of interior to edge habitat.
Well, fragmenting the landscape makes a whole lot of edges.
Exactly.
So they can live in those edges.
Right, and the generalists are the ones that tend to populate the edges. And the more fragmented the landscape is, the higher the proportion of edge habitat that you have, and therefore you end up with a greater overabundance, really, of those generalist species. And when fine-scale fragmentation occurs, it tends to favor those generalist species over specialists due to, again, that increased ratio of the edge to the interior habitat that results. And those same generalist or multi-habitat species are also going to be highly favored under three other mosaic patterns. The first one is in areas of convergency, where three or more habitats come together. Those generalist species are going to predominate. And likewise, they'll be favored in landscapes with numerous adjacencies of lots of different habitat types, and in mosaics where the habitats are scattered throughout the landscape rather than aggregated into larger patches, right? And all of these tend to describe, maybe not the convergency so much, but definitely the adjacencies and the interspersion describe human-dominated landscapes. And so those are some of the other factors that are favoring those generalist species. Under ideal conditions, both the specialist and the generalist species are able to thrive when the overall grain of the mosaic is more coarse, providing an interior habitat for the specialists and then the fine-grained areas that are interspersed within the landscape that give habitat to the generalist species, as well as space for concentrated areas of human development. So all three can coexist if we adapt with more ecologically friendly development patterns. So in cases where larger patches are set aside as conservation areas, They may come under threat from nearby suburbanization, which tends to introduce invasive plants, as we've talked about previously, and animal species. And in those situations, a buffer zone with strict controls on invasive species can be created between the area of development and the conservation area to help keep those invasives from infiltrating the reserve. And while this approach may be appropriate for large reserves adjacent to developing areas, there are also ways in which we can protect and improve the ecological value of remnant patches that are completely contained within large urbanized areas. And that is the subject of this final, let's see if we have time for it. We should have time for this. That's the answer to, or that's a question that's answered by this researcher, Andrew Gonzalez, who looks at how you can rebuild some of these sort of ecosystem networks in urbanized areas.
We are living in the century of urbanization. By 2050, 70% of the world's 9 billion people will be living in cities. Cities form a vast global network connected by flows of energy, food, information. This global network is the challenge of the 21st century. How do we make more sustainable cities with smaller ecological footprints and more equitable human well-being? Today, I want to stress the linkages between cities and ecosystems. Cities rely upon the goods and services produced by biological diversity embedded in ecosystems. These benefits are called ecosystem services. But as cities draw upon these resources, not only do they clear the land and transform the landscape, but they also fragment and disconnect ecosystems. This loss of ecological connectivity erodes biological diversity and degrades the very ecosystem services we need for sustainable cities. This happens at a global scale. There are global teleconnections between cities and landscapes, but it also happens at the scale of a city. So here I'm showing you analysis we did of how ecological connectivity, shown in red here, has been eroded over 50 years for the city of Montreal. So you can see this red pattern is dissipating. Patterns of growth like this are common the world over, and they are diminishing the contribution of ecosystems to city sustainability. What we have here is a non-linear relationship between urban growth and urban connectivity and ecological connectivity on the other hand. It describes a tipping point, a non-linearity in which beyond a certain threshold of urban connectivity, we lose the ecosystem's connected properties. We need science that can slow and even reverse tipping points like this. My research group at McGill University has used theory and experiments in the lab and the field to demonstrate how disconnecting ecosystem networks erodes diversity, limits productivity, and affects their adaptability. But we can use network science to reconnect them. And if we reconnect them, we can restore many of these properties in time. At the scale of entire cities, we're collecting data to show how ecosystems embedded in cities, like Singapore, affect air quality, urban heat extremes, and biological diversity and how it mediates processes like pollination, pest control, and the microbes that affect the well-being of our very immune systems. Back in 2009, I received a remarkable request from the Quebec government. They asked if I would apply my research to the design of an ecological network for Montreal and the region, the 27,000 square kilometer region around it. I can imagine I was a little bit daunted by the scale of this request. I hesitated. But after some hesitation, I realized that I had to do it. I think network science is both profound and practical. So how do we do that? We combine biodiversity science and network science and many different land cover data on habitat quality, ecosystem quality, and the needs of many species. And then we combine projections from regional climate models and our own land use change models to assess how connectivity has changed in the past, how it is today, and how it will be in the future. Our methodology allows us not only to identify connectivity, but also estimate the contribution of each ecosystem to the connectivity of the whole system. So we have like a weighting, which fragments are more important or less important to the connectivity and the contribution of services to the whole. So here I'm showing you one such map. The resolution is 30 by 30 meters, And I'm showing you the contribution of every pixel to the connectivity of the region's network. And in dark green, you see the ecosystems of high value, high connectivity, and zones in red of low connectivity. But what will the region look like in 2050? Here I'm showing you a scenario, a business as usual scenario, in which land use change and climate change have continued unchecked. Now you see many fewer dark green fragments, and the region's ecological connectivity has passed the point of sustainability. We can also use our methodology to identify ecosystems that contribute multiple benefits. So in this instance, on the left there, I'm showing you ecosystems in light green that not only maintain biodiversity, but they also mitigate urban heat extremes, which cause fatality in the summer months. This approach has allowed us to start a new discussion with government, with the city and NGOs and businesses, because we can show them that by protecting just 17% of this network, we can maintain 75% of the region's connectivity. So we're working with these partners and stakeholders to revision the city's greenbelt as an ecological network. Science like this, I think, should be applied to any city. That's my vision. I think we should be exporting this method to any city in any part of the world. Connectivity science and managing connectivity as cities grow will be an essential part of the solutions for urban sustainability in the 21st century. Managing ecological connectivity is one set of the solutions that I think is essential for sustainability, and sustainability ultimately is fundamental to our collective connected futures. Thank you very much.
All right, so that was kind of a very fast overview of the research that he's doing, but essentially it's looking at how you can apply value to different types of connectivity within that overall structure and that overall network, right? Because we're always going to need large patches for those interior species, but the key, particularly in urbanized areas, is how do you reconnect those areas with that network so that you can provide for a more sustainable and resilient populations of some of those species that are of high conservation value. And so that's looking at how you can use, in his case, the science of networks, basically, and understanding how networks operate to create optimal solutions for reconnecting some of these larger patches. So there's kind of a lot of interesting research going on and a lot of different approaches at how to solve some of these problems of restitching some of these landscapes back together. But again, they're all looking at these issues from that overall larger, I can stop this share actually. Looking at it from that larger overall scale of the entire mosaic and understanding the pieces of that mosaic and how they interact with one another. So that's something that we'll be thinking about a little bit more as we get into the final weeks of the semester. On Thursday, I'm going to be introducing a final project assignment, and we'll be moving on to begin talking about some of the metrics that are used to measure landscapes and how we can begin to quantify some of these different factors that we've been talking about over the past few weeks. So any questions or comments before we adjourn? All right. Have a good one, and I'll see you guys on Thursday.
Thanks, Scott.
Bye.
Thank you.
Thanks, Scott.